For those of you that don't know me, I'm Steve Sandler, and I am the founder of Picotest, and I'm very active in the world of power integrity. And currently, it seems like everybody wants to be talking about AI data center and HPC, and in particular, the challenges and solutions that we have around power integrity. So that's what I'm going to be talking about today. And one of the things that's really interesting about the AI data center in HPC space is how fast it's growing and scaling. And because of that, we're facing, I think, more challenges in that arena than in many others. And these challenges are in different places. And I'm going to talk about all of them today, but certainly printed circuit board design, cooling, SIPI, and measurement. And I think all of those are presenting challenges. And as the core domain currents are now up to about 2000 amps or so, we've reached the limits of many of the measurements and techniques and skills that we've acquired over the last decade or so. And I think that's where many of the challenges are coming from. And it's also spurring an awful lot of innovation. And so today I'm going to talk a little bit about all of those different things. And so, kind of, here's our agenda. We need to understand where it is that we are. What is the current state of the art, and what are we worried about for the next generation? And generations are happening really fast. So, what do we need to be planning for? A lot of the challenges are PCB related, and so I want to talk about those challenges and how we're working to mitigate them, and in some cases, how we don't know how to mitigate them, but maybe are just crossing our fingers. Some of the measurements that we've learned to make and that I've been teaching for decades that don't work in the current space, the current state of the art. And so, what are we going to do about that? What are we doing now? And what are the shortcomings? And what do we think needs to happen next? There's a lot going on in VRM design and topologies, and there's a lot of reasons for that. But it's kind of interesting because there are so many to talk about. So, we'll talk about that. And of course, all of this electronics requires cooling, and there's an awful lot going on in cooling. And of course, we are going to make sure that we have time for questions in the end. So save your questions because I really like hearing them. We have to start by understanding where we are. And I think that's essential to understanding the current state of technology and also the basis for where it is that we're going to be shifting from, right? We need a good reference point. The current core power rail for AI data center and HPC is sitting at roughly up to about 2200 amps, and that's occurring in a package size that's about 5600 millimeters squared. The typical operating core voltage is between zero point 0.7 and zero point 0.8 volts. And most of these designs use a two-stage lateral power delivery system. And by lateral, I mean that everything is on the same side as the ASIC. It's not backsided power. And this board in the picture, this is one of Picotest's demo boards, and you can actually see the two stages. Just above and just below the ribbon cable, you can see the two big, large power blocks, and those are the 48 volt to 12 volt converters. And then around the ASIC, you can see all of the little power modules, and those are 12 volt to zero point 0.8 volt modules. And then there's a digital controller that's on the far right side of the board. And this is what these HPC data center boards currently look like. And this doesn't mean that that's the maximum current. We are seeing boards as high as about 11,000 amps. We've seen 2,000 amps in much smaller packages than this. And yes, we have seen some 0.55 and zero point 0.6 volt core power rails. But this is kind of a current average state of the art is 2,000 amps, zero point 0.7 to zero point 0.8 volts. And this is moving really fast. So if we just look over the past year, Picotest introduced our first 2,000 amp tutorial at DesignCon about a year ago. Um, and in that session, we showed our board, which is a relatively large board. That one's about 14 inches by 14 inches, if I remember right. And you can see all the power blocks around the ASIC. That ASIC was 100 millimeters by 100 millimeters. And we did the first tutorial with that. It was really popular. 6 months later, that board had already shrunk down to something about the size of the new Hopper NVIDIA board, which is more like around 7 by 10 inches. Same 2000 watts, just much smaller. And the ASIC was still around 100 millimeters by 100 millimeters. And 6 months later, the board was the same size, but the ASIC had shrunk to 75 millimeters by 75 millimeters, or in this case, I think it's actually 72 millimeters by 75 millimeters. And it's still shrinking. Currently, we're seeing 2000 amp boards now at 50 millimeters by 50 millimeters. And so this is one of the challenges that we're facing is just that things are moving really fast. And just as we think we nailed it, it changes. So one of the questions I get a lot is, where does it stop? And the answer is that unfortunately or fortunately, depending which side of the line you're on, it doesn't. It just keeps going and going and going, sort of like the Energizer Bunny. We've actually even heard about 2000 amp chips that are 25 millimeters by 25 millimeters. And we've heard that the new Cerebras wafer is at 33,000 amps. So it's not going to stop. It's just going to keep going. And our job as engineers is to try to figure out how to keep up and just keep supporting.